We were talking about different sampling schemes last time. We went through a whole bestiary of different ways of drawing samples. We're now going to focus on a couple of the simplest ways of drawing a probability sample. So our big dividing line, the big bright line, is between probability samples and non-probability samples. And in non-probability samples, we have things like samples of convenience, quota samples, systematic samples, so forth and so on. In probability samples, we have a wide variety of things, the simplest of which is a simple random sample, which is it's like putting a ticket for every individual in the population into a big hat, stirring up the tickets really, really well, and pulling out little n tickets from the hat that contains big N tickets without replacement. Now, I should maybe mention in passing that that's actually a terrible way to draw a random sample, that to put tickets into a hat and try to stir them up, or to put ping pong balls with labels on them into a big bucket and stir them up is really not a very good way to do it. The reason being that it's very difficult to mix things thoroughly mechanically. And this actually came up in the Vietnam draft lottery, that people's names sort of went into the hat and they ended up not getting stirred up very well. And so if I'm remembering correctly, if your birthday was towards the end of the year, you were much more likely to be drawn in the lottery because those were the names that went in last and they didn't stir things up very well. So physically randomizing things is hard. What we do in practice and statistics might be to generate a random seed by rolling dice or tossing coins or using something like that, and then from that random seed to use a pseudo-random number generator, an algorithm that produces a sequence of numbers that behave very much like random numbers, but not exactly like random numbers. They are, in fact, predictable. There's an algorithm that's used to generate them. So if it ever falls to you to draw a random sample, you probably don't want to do it by putting names on tickets and putting the tickets in a hat and stirring them up, just because it's very difficult to do that in a way that ends up being fair. It's also very difficult to verify that there's exactly one ticket for each person in the population, for each item in the population in the hat. If you're going to do it using a pseudo-random number generator, you want to avoid using things like Excel. Excel's random number generator is broken. You want to be careful to use a high-quality pseudo-random number generator, and if that ever comes up, then you can start, look for things like the Mersenne twister algorithm. There are other things that are very good as well. Anyway, all right, so on the side of drawing probability samples, we have a simple random sample. We have random samples with replacement. Both of those have the feature that every item in the population has the same probability of being selected. Systematic random sample, every item in the population has the same probability of being selected, but not every subset of the population has the same probability of being selected, right? So it's simple random sample has the distinguishing characteristic that every subset of little n of the capital N objects in the population is equally likely to end up being the sample. We talked about cluster samples, multi-stage samples, stratified samples. There are random versions of all those, stratified random samples, so forth and so on. We're just going to concentrate on the simplest cases, which are simple random samples and random samples with replacement. Okay, so we want to learn something about a population. We want to know what's the average income of some group, what's the average height of some group, what are people's opinions on some issue, whatever it is. And we're going to learn about that by drawing a random sample from the population, a simple random sample, and figuring out what's true for the sample and trying to extrapolate from the sample to the group. Now, our ability to do that and to understand the size of the error we're likely to commit by extrapolating from the sample to the population is going to depend on how the sample is drawn, and it's going to depend on what we do with it. For a probability sample, you can generally quantify the likely size of the error in extrapolating from the sample to the population. For a non-probability sample, all bets are off. You cannot typically quantify the size of the error that you're going to commit if you try to base an estimate for the population on something computed from the sample. All right, things that you compute from the sample are generally called statistics. We talked about this once upon a time. The difference between a parameter and a statistic. A parameter is a property of the population. A statistic is something you compute from data, something you compute from a sample. There's a particular if the statistic is being used to estimate something about the population, it's called an estimator. So an estimator is basically a rule for assigning numbers to samples. And so an example of an estimator is the sample mean. The sample mean assigns a number to a sample. It takes the average of the values of the units that you get in the sample. That's the number it assigns. What's it used for? Why is it called an estimator? Well, it's used to estimate the population mean. Okay, so we've got some population of items. Okay, this has some true population mean. We're going to draw, say, a simple random sample of size n from this population that has capital N items. From that, we could compute the sample mean. And the sample mean would be an estimate of the mean of what's in the box, the population mean. But it's not going to be a perfect estimate because the value of the sample mean isn't always the population mean. In fact, typically it isn't the population mean. What value you get for the sample mean depends on which random sample you happen to get. The value for the population mean is always the same, right? It's just some number. So how can we figure out how far off the sample mean is likely to be as an estimate of the population mean? We're going to talk a little bit in general about how do you grade estimators? How do you tell whether one is better than another or not? How do you score them? And then specialize that to looking at the sample mean and the sample percentage, which are the most commonly used estimators. Okay, so generally, you can think of, we've got some true parameter value that we want to estimate. So population parameter. And we've got some estimate. Some estimator from a sample. Okay. The difference between those, what the estimate is minus the true value, that's the error, right? That's the error that the estimator made in a particular case for a particular sample. Okay. This is a random quantity because the value that the estimator takes depends on the random sample, depends on which sample you happen to get. Right? So how do we tell whether an estimator is good? Well, in any particular case, we're not going to know the value of the population parameter, but we can think about some properties of the estimator. In particular, we might be interested in this difference. Right? And that difference is a random variable because this is a random variable. Right? If the estimator is random, and the estimator minus a constant is random. And if we want to know if that error is now a random variable, we want to know, is that error big? Is that error small? Right? Does it tend to be big? Does it tend to be small? What would be a way of summarizing that? We could take its expected value, right? So we could take the expected value of that difference. It's a random variable. This number is always going to be positive, right? This measures how far off the estimator is. And if this thing is big, the estimator isn't very good. If this thing is small, the estimator is good, right? Because if this thing is big, the estimator tends to be far away from the thing it's trying to estimate. If this thing is small, it tends to be close. Now, it turns out to be easier to do calculus and analyze things if you work with the square instead of with the absolute value. It's arbitrary. This is one particular way of measuring how good an estimator is. And this particular thing is called the mean squared error. Mean squared error of the estimator. Okay, it's the expected value of the difference between the estimator and the thing it's trying to estimate squared. Now, remember that the expected value of x squared is generally not equal to the expected value of x squared. Right? This is not the same thing as the square of the expected value of the absolute value. It's the expected value of the square. This is in general. Okay. So there are other ways of thinking about this. And here's one of them. Imagine that you have a target, and you're shooting at the bullseye. Okay. There are two kinds of inaccuracies that your rifle can have. All right? One kind of inaccuracy is when you shoot repeatedly, the bullet hits in almost the same place every time, but that place is not the bullseye. Does this make sense? Okay, so this is an accurate rifle that is not sighted incorrectly. Okay, you could adjust the sight so that those shots, if you did it again, those shots would all be really close to the bullseye. All right, this difference, how far off you are on average from the bullseye, that's called bias in statistical terms. Okay? The spread of the shots, that uncertainty, how spread out they are from each other, that is variance or standard error. Okay, so you could have a different rifle which when you shoot, thank you. Is all over the place, right? This one, it might be that if you average the location of the shots, they would average to be the bullseye, right? That somehow the centroid would be the bullseye. So this second rifle has low bias because on average you would have hit the bullseye, but it has high variance. It has high standard error because you're typically really far away from the bullseye. It's a different kind of inaccuracy. One is sort of an intrinsic inaccuracy in the process. It's not repeatable. And the other is it's repeatable, but it's off from the mark. Okay, so in this example, you have low standard error, big bias. In this example, you've got low bias, big standard error. And they both correspond to large mean squared error. So in fact, you can write the mean squared error of an estimator is equal to the bias of the estimator squared plus the standard error of the estimator squared. All right, what is the bias of the estimator? The bias is defined to be the expected value of the estimator minus the parameter. Okay, with no absolute value sign. All right, it's just on average, what does the estimator give you? How does that compare to the parameter? So remember, expectation is linear. So this is equal to the expected value of the estimator minus the expected value of the parameter. What's the expected value of the parameter? It's just the parameter itself, right? Because the parameter is a constant. So the expected value of a constant is a constant. So this is just the parameter. All right, so let's go back to thinking about the sample mean. From a simple random sample, what's the expected value of the sample mean for a simple random sample? It's, sorry? We have an answer, but a shy answer. I think it's the mean of the numbers in the box. It's the population mean, right? If we're using the sample mean as an estimate, so if we're trying to estimate the population mean, and we're doing it using the sample mean, what's the expected value of the estimator? It is the population mean, right? Because the expected value is the average of the numbers in the box, right? The expected value of the sample mean of a simple random sample or a random sample with replacement is just the mean of the numbers in the box. It's the population mean. So the bias of the sample mean as an estimate of the population mean is 0 because the expected value is the population mean and the parameter is the population mean. Those things just cancel, right? Okay. So if that's the case, what's the mean squared error of the sample mean as an estimate of the population mean? We're talking about a simple random sample. Well, the bias is 0. Bias squared is 0. The standard error of the sample mean as an estimate of the population mean, well, in this case, it doesn't matter. It's just the standard error of the estimator. What is the standard error of the sample mean for a simple random sample? Okay, we've got SD box over root n. And this is a simple random sample, so there's one more thing in that. Yep. So SE of the sample mean for a simple random sample is equal to finite population correction times the SD of the box over root n, where n is the sample size, and f is the square root of n minus n over n minus 1, where n is the population size. Ring a bell? Okay. All right, so the mean squared error of the sample mean as an estimate of the population mean is just the square of its standard error, which is just this thing squared. Okay, because the bias, it's an unbiased estimator. If the bias is 0, it's said to be unbiased. This is an unbiased estimator. Okay, and then a special case of this is the sample percentage, right? The sample percentage is a special sample mean. Sample mean if the population only contains 0s and 1s. And in that case, so the SE of the sample percentage for a simple random sample, we're still going to get F. SD of the box now has a simpler form. What's the SD of the box? In terms of the fraction of 1s in the box? Uh-oh. So ring a bell if you have a box, it's a 0, 1 box, has a fraction p of 1s. What's the SD? Not ringing a bell? The SD of the box is square root of p times 1 minus p, where p is the fraction of 1s in the box. This, okay. All right. Okay, so this is the special case that the population we're drawing from only contains 0s and 1s. And so p is the fraction of 1s, portion of 1s. Okay? So if we drew a random sample from a box of numbers, simple random sample, we calculate the sample mean, we get some particular value. This is the sample mean. What does that tell us about the population mean? Could the population mean be here? Could it be here? Yeah. Could it be here? Yeah. We don't know exactly what the population mean is. But what do we know? We know that typically, if this is the population mean, the sample mean is going to be within about an SE of the population mean. Okay? Sometimes more, sometimes less. But the average distance from the population mean to the sample mean is about an SE, is an SE. Okay? And so if we observed that the sample mean was this, and we knew the standard error of the sample mean, then a reasonable estimate would be that the population mean is the sample mean give or take about an SE, plus or minus about an SE. Right? That's kind of our chance variability due to the luck of the draw. Okay? This isn't a quantitative statement yet. It's qualitative. We're going to make it quantitative later. Okay? So the sample mean isn't going to be exactly equal to the population mean, but typically it's off by about 1 standard error. Now, how do we use that here? In order to know what the standard error is of the estimator, we need to know these things. We need to know F. We need to know the SD of the box. We need to know the sample size. We know the sample size. We're pretending that we know the number of numbers there are in the population, the size of the box, size of the list of numbers of the box. But we don't know the SD of the box. Right? Okay. You remember once upon a time we had some exercise where you, like, if you, oh, maybe that's coming up, actually. You're asked if the SD of the box can have only 2 values if you have a 0, 1 box and you're told what the variance is. Maybe that's an upcoming problem set. It's all a blur. Okay, so what can we do about the fact that we don't know the SD of the box? Well, if we were talking about a general population of numbers, the SD of the box could be arbitrarily large. Yep, there's no sort of upper bound. We can't really get a bound on the error, right? We could have a box that has all 1 number in it, in which case the SD of the box is 0. We could have a box that has the numbers minus a million, plus a zillion, whatever, and the SD of that box would be enormous, right? So if we don't know what's in the box, we're not going to know the SD of the box. We need some ways of getting around that to try to figure out what the uncertainty in the sample mean is. So we're going to look at a couple of different approaches. So the first approach we're going to look at works for 0, 1 boxes, because for 0, 1 boxes, the standard deviation of the box can't be just anything. It actually is within some limited range, and we can make a worst-case assumption. So once upon a time, bless you, we talked about the fact that if we look at the square of the SD of a 0, 1 box, so the SD of a 0, 1 box is equal to the square root of p times 1 minus p. This rings a bell, yes, now. Didn't 5 minutes ago, but now it does. Okay, and so the SD squared is equal to p times 1 minus p, which is p minus p squared. And we could write that as minus p squared plus p if you want. And this is the equation of a parabola, right? Okay, and because the leading coefficient is negative, it's a parabola that has a maximum, right? And as p goes between 0 and 1, this thing goes up and attains its maximum at 1/2. And what is that maximum? Can we plug in? It's a quarter, right? Okay, right? Okay, if we plug in 1/2, this is minus 1/2 squared, which is minus a quarter, plus 1/2 is a quarter. Okay. And how do we know that the maximum is at 1/2? We could do 15 seconds of calculus, differentiate this. We get minus 2p plus 1 equals 0. Okay, so p is equal to 1/2. It would be the stationary point. All right, okay, so if we have a 0, 1 box, the SD of the box, so what does this say about the SD of the box could be 0. The box could contain all 1s or could contain all 0s, in which case the SD of the box is 0. The SD of the box could be bigger than 0, but the biggest it could be is 1/2, which is what you get if you plug in 1/2 here. You get the square root of a quarter, which is 1/2. All right? So we don't know what it is, but it can't be bigger than 1/2. So if we're drawing from a 0, 1 box, and we're looking at the sample percentage as an estimator of the population percentage, then we know that the standard error of that as an estimate, we know sort of how far off it's likely to be, isn't going to be any bigger typically than the finite population correction times 1/2 divided by the square root of n, because this can't be bigger than 1/2. Does that make sense? We're going to be off by some amount. It's a random amount. We can't say how big it is in any particular case unless we already knew what was in the box. But the amount by which it's likely to be off, in the worst case, the problem is I'm mixing likely and worst case. So if the worst possible things were in the box, then the amount by which it would be likely to be off would be like f times a half over root n. Okay. For other mix of things in the box, then the amount by which it's likely to be off is less than that. So far, so good? Okay. So this is a worst case upper bound on the SD of the box. It works for 0, 1 boxes only. Right? It doesn't work if you have a general list of numbers in the box. Okay. What if you do have a general list of numbers in the box? What then? Well, if the sample size is really big, okay, so first, let's back up slightly. This, pretending that p is a half to get a worst case scenario here, can be very, very pessimistic, or it can be about right. It depends on whether the true value of p actually is really close to a half or is close to 0 or 1. Okay, if it's close to 0 or 1, then this is going to be really crude. And if it's close to a half, then this is going to be really good. We're all together? All right, if we had a really big sample, then our estimate of the sample percentage would likely be, our sample percentage would likely be a pretty good estimate of the population percentage. It would likely to be pretty close to the population percentage. So if it is close to the population percentage, then the SD of the box would be close to what I would get if I plugged in the sample percentage in place of the population percentage here. Okay, so I'm going to say, suppose that my estimate is I'm going to use a Greek letter phi for the sample percentage. So this is the number of the ones in the sample divided by n. Okay? So that's our estimator. It's an estimator of the population percentage. And if phi is close to p, then the square root of phi times 1 minus phi is close to the SD of the box, right? Because the SD of the box is p times 1 minus p, okay? So this number is called the bootstrap estimate. Of the SD of the box. Okay, it's called a bootstrap because you've heard of the notion pulling yourself up by your bootstraps. Okay, like how do you get up with nothing to stand on? You pull yourself up by your bootstraps. Okay, how do you figure out what the SD of the box is when you don't know what's in the box? Well, you pretend that the sample is what's in the box, and then you pretend that the sample percentage is the true population percentage, in which case this would be the SD of the box. Okay? This estimate is not likely to be very good if the sample size is small. If the sample size is big, this is likely to be a pretty good estimate. The sample size is small, like 3, 5, 10, something like that. It's probably not very safe to use this as the estimate of the SD of the box. You should stick with the worst case estimate, pretending that p is 50%, okay, which will give you something conservative. But if the sample size is 100 or 1,000 or 5,000, then the sample percentage ought to be pretty close to the population percentage, and the bootstrap estimate of the SD of the box ought to be pretty good estimate of what's actually in the box, the standard deviation of the box. This all right with everybody? Yeah. Little n is the sample size, right? This is the sample percentage, so it's how many ones are there in the sample divided by how many things you looked at. Okay. So far, so good? Okay, this this bootstrap estimate of the SD of the box, I think I'm calling S star. Yep. Okay. So we're calling this thing, the bootstrap estimate is going to be denoted S star. S star is the square root of the sample percentage times 1 minus the sample percentage. Okay. All right. This idea of pretending that the sample is like the population in order to figure out what the SD of the population is like in order to figure out what the standard error of your estimator is, right? So the next step from here, having estimated the SD of the box to be this, we could now use this to give an estimate of the mean squared error, an estimate of the standard error of the estimator, right? What would our estimate of the mean squared error be based on this? We know that the sample percentage is unbiased, so we don't need to worry about this term. This term is 0. But our estimate of this term would be what? Okay, so for the sample percentage of a simple random sample as an estimate of the population percentage, what do we know? That the bias of that estimator is 0. The standard error of the estimator is equal to f times the square root of p times 1 minus p over root n. And we know that that is less than or equal to f times a half over root n, right? Because we know that this can't be bigger than a half. And we know that if the sample size is large, then this ought to be about the same as p. And so the SE of the sample percentage ought to be about f times sample percentage 1 minus the sample percentage over root n. Okay? So this is what it really is, but we don't know p. So we don't know what it really is. No matter what p is, it can't be bigger than this. If our sample size is pretty big, then it ought to be pretty close to this. This all makes sense? Okay. Now, this move of saying, I don't know what's in the box, but I'm going to estimate the standard deviation of what's in the box by the standard deviation of the sample, right? That I can do even if the box has numbers other than 0 and 1 in it, right? That doesn't rely on the numbers in the box being only 0 and 1. What we needed for that was to get this upper bound. But this approximation isn't relying on the fact, the idea of taking, this is the SD of the sample, right? The SD of a list of zeros and ones is the fraction of zeros times, fraction of ones times the fraction of zeros, square root of that. Yep. Okay, so, sorry, I didn't quite close the loop here. What would our estimate of the mean squared error be then? We know it's not bigger than this thing squared. And if the sample size is big, it ought to be about this thing squared. Okay? That's what it's this term that we're worrying about. Okay, so back now we're pulling numbers from a general box, and we could estimate that if n is big, then SD of the sample, should be close to the SD of the box. Okay, I'm not going to make this a quantitative statement, but just sort of if the sample is sufficiently large, then this ought to be a good approximation of that. So that leads to this general notion of S star is equal to the SD of the sample. And this is commonly used in sampling from a 0-1 box to estimate the SD of the box. It turns out that something slightly different is typically used if you're drawing from a box that isn't a 0-1 box. And instead of this, what's used is the following, which is called S, which is the sample SD. And it's equal to basically S star times root n over n minus 1. Okay, let me write out what that definition gives us. And those of you who have had statistics before are used to calling this the standard deviation. Okay, so S is, if we have a list of data, x1 up to xn, and let's say that the mean m is equal to x1 plus x2 plus so forth plus xn divided by n. That's the sample mean. Then the way we form S is we start by taking the residuals between the data and the sample mean, squaring them. Okay, and we want the RMS of the residuals. If we were taking the ordinary SD, we would be dividing this by n, right, to find the mean of the squares, and then we would take the square root of that. The difference between S star and S is that with S, instead of dividing by n, we divide by n minus 1. And then we take the square root of the result. Okay, so this thing with n minus 1 in the denominator is what many of you have seen before as the standard deviation, but it's actually the sample standard deviation. Notice that the sample standard deviation is not the standard deviation of the sample. They differ by a little bit. If n is really, really, really big, then this ratio is going to be almost 1, right? The limit of this ratio as n goes to infinity is 1. Right? If n is small, then this thing is going to can be noticeably bigger than 1. So this sample standard deviation is bigger than the standard deviation of the sample by an amount that gets smaller the larger the sample is. So far, so good? Okay. Why would you want to estimate the SD of the box by this rather than by the SD of the sample? So there's a technical reason, but I'll try to explain the heuristic behind it. So when I calculate the sample mean of a list has a special property, right? The sample mean is the number that minimizes the sum of the squared deviations, right? It's the number from which the sum of the squared deviations is smallest. Right? So if instead of plugging in the sample mean here, I plugged in the mean of the box, then what would happen to this sum of squares? Would it get bigger or smaller? I've got a list of numbers that are sampled from the box. In one case, I'm subtracting from that sample the mean of the sample. In the other case, I'm subtracting from that sample the mean of the box. Which is going to give a larger sum of squares? The mean, if I put it, if m is equal to the mean of the sample, or if m is equal to the mean of the box? Okay, the mean of the box is in general going to give me a larger sum of squares than the mean of the sample, because the mean of the sample is the number that makes that as small as possible. The mean of the box isn't typically going to make it as small. Okay? So if I'm trying to figure out how scattered things are around the mean of the box to find the SD of the box, but I don't know the mean of the box, and instead I plug in the mean of the sample, the scatter around the mean of the sample is going to tend to be a little too small. Okay? So by blowing it up by this factor, I get it to be back to be about the right size. Okay? This is going to tend to underestimate the scatter in the box because I'm looking at the scatter around that quantity around which the scatter is smallest, rather than the scatter around the mean of the box. So far, so good? Okay, so the technical story is the following, that S squared is an unbiased estimator of SD of the box squared for sampling with replacement. Okay, so what does unbiased mean? It means that the expected value of this is equal to this. Okay, and that's true in a particular case if the sample, it's true if the sample is drawn with replacement. Why should this matter? Okay, so first of all, S squared is unbiased for the SD of the box squared. Does that mean that S is unbiased for SD of the box? If S squared is an unbiased estimator of this, is S an unbiased estimator of that? Not necessarily, right? Okay, so typically not, in fact. So S squared is unbiased for SD of the box squared. That doesn't mean that S is unbiased for SD, right? Moreover, we're talking about simple random samples. We're sampling without replacement, not with replacement. So what happens under sampling with replacement seems like it's a little off base. Yep. Nonetheless, this is what it is traditional to use to estimate the SD of the box. Okay? It's in the situations where the sample size is large enough that you can rely on this as being a pretty good estimator, the difference between n and n minus 1 isn't going to matter noticeably. Right? N's going to be big. All right, so we've got the conservative bound on the SD of the box for a 0-1 box. That is, the SD of a 0-1 box can't be bigger than a half. We have the bootstrap estimate of the SD of a 0-1 box, S, which is based on substituting the sample percentage for the actual percentage, pretending that the sample percentage is exactly right. And then we have the generalization of that to the bootstrap estimate for a box that has things other than zeros and ones. And then we have the slight variant of that, the sample standard deviation, which divides by n minus 1 instead of n before taking the square root. Tends to be slightly larger And it has this funny characteristic that it's an unbiased estimate of the SD of the box squared. So let's do a little simulation here. Okay, S squared is called the sample variance. And I get this. Okay, so this is our sampling applet as before. We've got the numbers 0 through 10 in the box. But now what we're calculating instead of the sample mean or the sample sum is we're calculating S squared. When we draw a sample, each time we draw the sample, we're going to calculate this thing I've just covered up. That is the sum of the squares of the residuals from the mean divided by n minus 1 and not taking the square root. We're looking at S squared because it's S squared that's supposed to be unbiased for the standard deviation of the box. So the SD of the box is 3.16. Okay, the square of the SD of the box is 3.16 squared, which is about, let's start by drawing with replacement. Is that going? Oh, yeah, okay, that's right. Okay, which is 10. Okay, and so here we are. We're going to take a sample. What was that? That was a sample of size 5. We drew 5 numbers at random with replacement from the box, calculated S squared, the sum of the squares of the residuals from the sample mean divided by 5, and then that's it. That's what we got. So we can do this a bunch of times, and let's speed it up. Okay, so now we've drawn 10,000 samples of size 5 and plotted a histogram of what values we got for S squared. And if you look at what happens, sometimes you get a very big value. Typically you get, kind of a moderate value. The mean of those 10,000 values that we got, 10,000 values of S squared, was just a little bit less than 10. The expected value is 10, right? The square of the SD of the box. Okay. Now, if we draw the random sample without replacement, then it turns out that S squared isn't unbiased for the SD of the box squared. It's unbiased for a thing that involves, when you're calculating the SD of the box, instead of dividing that by the population size, you divide by the population size minus 1. So it kind of corresponds to the same denominator in some loose sense. So if we go to sampling without replacement, now if I'm taking something that's like the SD of the list, but instead of dividing by the number of items there are on the list, I divide by 1 less, the result is going to be bigger, right? Smaller denominator, bigger ratio. The expected value of S squared for sampling without replacement is a little bigger than it is for sampling with replacement. Okay, and in this case, it ought to be 11. So if we do this experiment, another 10,000 draws from this box, this ends up being very, very close to the expected value. Okay, the average value of S squared for drawing with replacement from this box drawing without replacement from this box turns out to be very, very close to its theoretical value, which is bigger than the SD of the box. Okay, so far, so good? Okay. Just let's all right, so just to summarize where we are right now, we're thinking about drawing a random sample from a box of numbered tickets. If we're drawing without replacement, then the standard error of the sample percentage is no larger than the finite population correction times 50% divided by the square root of the sample size. If we're drawing with replacement, then the corresponding value of f is 1, right? The finite population correction won't matter. It's 1. We don't need it. And the resulting standard error is no bigger than 50% over the square root of n. Okay? Now, that's likely to be an overestimate of the SD of the box because it's a worst-case assumption. It pretends that you have 50% zeros, 50% ones in the box. We could estimate it instead using the bootstrap estimate. If the sample size n is big enough, then S star, the SD of the sample, is likely to be pretty close to the standard deviation of the box. And as a result, S star over the square root of n is a good estimate of the standard error of the sample percentage if you're sampling with replacement. It'd be f times S star over root n if you're sampling without replacement. It's more common if you're talking about drawing from a general box rather than a 0, 1 box to use S, the sample standard deviation, rather than S star, the standard deviation of the sample. It makes sense primarily if you're sampling without replacement, because that's the situation under which S squared is unbiased for the square of the standard deviation of the box. Okay, if you're sampling without replacement, you modify these by multiplying by the finite population correction. In the particular case that you're taking a random sample with replacement, the sample standard deviation squared is an unbiased estimate of the square of the standard deviation of the box. Who cares? I don't know, but it's common. That's what people tend to do. So far, so good? Should we try to make this a little concrete by doing an example? I especially want to do a bunch of arithmetic, though, so let's see what makes... We'll just talk through this example. Are there any questions? Okay, we're looking at a population of 6,000 people. We've drawn a sample of size 12. Simple random sample. Does that mean with replacement or without replacement? Without replacement. Simple random sample is without replacement. Okay? If we have a box that has 6,000 weights in it, is that a 0, 1 box? No, right? Weights can be anything non-negative, right? Can't have negative weights, but other than that, we don't know a whole lot. All right, so here is a sample of 12 weights drawn from that box. And what we want to do is estimate the average weight of the population and estimate the error of our estimate. Okay, so our estimate of the average weight of the population would be the sample mean, right? This is our sample. The sample mean is an unbiased estimate of the population mean. So adding these 12 numbers together and dividing by 12 is the sample mean. And if we do that, the answer is 128.447. So that's our estimate. But we know that our estimate is not likely to be exactly right. It's going to be off by something. Question? Yep. Okay. All right. So it might be too big. It might be too small. We don't know which in any particular case unless we knew the 6,000 numbers that were in the box, right? But what's the sort of give or take number that ought to go with this estimate of 126.447? Typically, how far off would the sample mean of a random sample of size 12 from these 6,000 numbers be from the mean of the 6,000 numbers? So we can use these 12 numbers to try to get a handle on the SD of the box. The amount by which our estimate is likely to be off is a standard error. The standard error is going to be f times the standard deviation of the box over the square root of n. We don't know the SD of the box, but we can estimate it by the SD of the sample. Not going to be a perfect estimate, and in fact, for a sample of size 12, it's probably not even going to be a very good estimate, but it's something we can do nonetheless. So because this is not a 0, 1 box, we're going to tend to use the sample standard deviation S rather than the standard deviation of the sample S star to estimate the SD of the box. Okay? So what would we do? We need to find the sample standard deviation, which involves doing this calculation that I've covered up. We need to take the sum of the squares of the residuals between the data and the sample mean. Divide that by the sample size minus 1, 11, and then take the square root of the result. So these are the data again. From each datum, I need to subtract 126.447 and square the result. Okay, so this is 118.72 minus 126.447 quantity squared. Okay, so we'd add up these 12 numbers and divide by 11 and then take the square root, and that would be our estimate of the SE of the sample mean. Oh, sorry, we multiply by the finite population correction, which is going to be very, very, very close to 1 because 12 is only a tiny fraction of 6,000. The sample size is only a tiny fraction of the population size. So the finite population correction is very, very close to 1. Does this make sense to everybody? Okay. All right, let's do this exercise. So a consumer advocacy group is concerned about the safety of child seats made by a particular manufacturer. They take a simple random sample of 200 of the 9,000 seats that were made by the manufacturer in a given year. 6 of those seats are found to have safety defects. Okay, which of these is a parameter? Is it the number of defective seats in the sample, the percentage of defective seats in the sample, the percentage of seats made by the manufacturer that year that have defects? C, right? The parameter is a property of the population, not a property of the sample. Right? Okay, so this is C. What's the sample percentage of defective seats? Six over 200, which we can, even in our heads, turn into a percentage. 6 over 200 is like 3 over 100, which is like 3%, okay? Okay. What would our estimate be of the fraction of seats that are defective in the population? This is not subtle. Not supposed to be subtle. We have the sample percentage. The sample percentage is a nice unbiased estimate of the population percentage. So why don't we use the sample percentage? 3%. How about 3%? Okay. That's kind of why we're calculating the sample percentage. We're calculating it to estimate the population percentage, and that's our best guess based on the sample. Well, if you were trying to estimate something other than a population percentage, you might not use the sample percentage to estimate it. Okay. As long as it's a simple random sample, or if it's like a different kind of sample from that? Well, if you're trying to estimate a population percentage, then you know that the sample percentage of a simple random sample or a random sample with replacement are unbiased estimators. Okay, so they would be reasonable estimators to use. If you're trying to estimate something other than a population percentage, then you probably don't want to use the sample percentage to estimate it. And if your sample is drawn in a way other than as a simple random sample or random sample with replacement, you need to take that into account. So if you're using a stratified random sample and the sampling fractions vary, so one stratum you're taking 1 out of 10 things, another stratum you're taking 1 out of 100 things, you want to take that into account because if you just use the sample percentage, it would be biased. Okay. So what we're talking about in this chapter is really just simple random samples and random samples with replacement. If you have another probability sample design, it's not this simple. Okay, what's our bootstrap estimate of the standard error of that estimate? Sorry? Okay, so our bootstrap estimate of the SD of the box is S star, which is going to be the square root of 0.03 times 0.97, right? Then how do we turn that into an estimate of the standard error? We need to multiply F times S star over the square root of n, right? So F is going to be the square root of 6,000 minus 200 over 5999, right, times this thing divided by the square root of 200. Oh, it was 9,000? I'm sorry. Oh, 9,000. Thank you. Okay. All right, so this would be our bootstrap estimate of the standard error, starting with the bootstrap estimate of the SD of the box. And what's the largest that the standard error, that sample percentage of defective seats, could be? The largest standard error could be. The largest the standard error could be for the sample percentage for this sample in this story. I feel like Robin Williams going rented lips. Yeah. Right. So we would just substitute the upper bound would be f times a half over root n. So it's again the same factor f, square root of 9,000 minus 200 was 200, wasn't it? Over 8999 times a half over the root of 200. Boy, my handwriting could use some help. Okay, so that's the largest that it could be. So far, so good?
So F is the population minus sample over n.
Yeah, so F is the square root of n minus n over n minus 1. Okay. All right. Again, as we were just saying, all the stuff we've been talking about applies just in the special cases of simple random samples and random samples with replacement. If you have a non-probability sample, none of these calculations make any sense whatsoever. And if you have a different probability sample design, like a stratified random sample, a multi-stage random cluster sample, something like that, these formulae won't be the right formulae. They won't give you the right answer for the standard error, et cetera. It's more complicated. We're not going to talk about that. It's a question. Okay, there's a couple things going on. This doesn't have anything to do with normal, but what you're saying is right. So let me see if I can just repeat the idea. So the following is true. The normal approximation to the binomial is best when p is equal to a half. That's true, and that's what I think you're remembering. That's because the binomial probability histogram is then symmetric, right? Okay, that's true, but it's irrelevant for this particular thing that we're talking about. Okay, what we're talking about is for what value of p is SD of the box biggest. Okay, and there it turns out that that answer is p is equal to a half. Okay. So it's this thing that we're using here. Other questions? Okay. Great. Let's start the next thing. We've been talking about sort of saying that if you have an unbiased estimator, then the value of the estimate is going to be, give or take one standard error, the truth, the parameter that you're trying to estimate. So our estimate of the population parameter would be, it's the estimate plus or minus about a standard error, okay? Because the estimator is likely to differ from the population parameter value by about a standard error, sometimes more, sometimes less. Well, we're going to try to turn this into a more precise statement now, a different way of quantifying error. We were talking about quantifying error by mean squared error in the previous chapter, and then mean squared error just reduced to the square of the standard error for unbiased estimators. And we were talking about two unbiased estimators, namely the sample percentage and the sample mean as estimators of the population percentage and the population mean. Okay. Now let's think about actually quantifying error in a different way. We're really going to give an estimate, give or take some range. We're going to give some range of values as our answer rather than a particular value as our answer. And we're going to calibrate it in such a way that our procedure has a big chance of producing a range of values that includes the true value of the parameter. So the idea is something like this. Here is the true value of the parameter. So this is truth. And we're going to give an interval as our estimate. And the interval is going to depend on the random sample. So the interval sometimes is going to be way out here, sometimes is going to be in here, sometimes is going to be down here. When the interval includes the truth, the interval is said to cover the parameter value. Okay? When the interval doesn't, it doesn't cover. Right? And what we want to do is we want to come up with a rule that gives us intervals that have a big chance of including the truth. So that most of the time, for most samples, the interval is going to include the truth. Sometimes you'll get a sample where the interval won't include the truth. But we want to say, for example, that 95% of the time, the interval that we get is going to include the true value of the population parameter. If we have a procedure that does that, gives us a random interval so that 95% of the time that interval includes the truth, that's called a 95% confidence interval. Okay? So how do we do that? Right? Well, what do we know about, let's start by talking about the population percentage because we can figure out the largest that the standard error of the population percentage could be. We're going to do something really, really, really conservative. We're going to use an upper bound on the SD of the box that comes from pretending that there's 50% zeros and 50% ones, because it can't get any worse than that. And then we're going to use Chebyshev's inequality to figure out how many standard errors away from the expected value the thing is likely to be, the estimate is likely to be. So here we know that if this is the true value of the population percentage, and we estimate it by the sample percentage, then what do we know? We can get lots of different possible values for this, depending on which sample we happen to get. But on average, they're plus or minus one standard error from the population percentage. How often are they more than two standards away from the population percentage? Sorry? 1 over 2 squared, yes. All right, so, okay. Is that up on the screen? Good job. Okay, right, so Chebyshev's inequality says that the probability that the sample percentage, which we're using the symbol phi, so let's use that, phi minus the population percentage p is bigger than or equal to 2, is equal to 2 times the standard error of the sample percentage, is less than or equal to 1 over 2 squared, right? Okay, in general, chance that it's more than k standard errors away is at most 1 over k squared. Okay? So chance that they differ by more than k SEs is no bigger than that. What's the chance they differ by more than k times a half over root n? Let's go ahead and put an f in here for grins. This number, f times a half over the square root of n, is that bigger or smaller than the standard error of the sample percentage? It's at least as big, if not bigger, right? So if the chance that this difference is bigger than this is at most 1 over k squared, what's the chance that it's bigger than this? Still can't be any bigger than 1 over k squared, right? 1 over k squared is still an upper bound? Okay. So what I know is the chance that the sample percentage differs from the population percentage by more than k times this bound is also no more than 1 over k squared. In fact, probably smaller, because this was already an inequality, and this is now plugging something even bigger in as the threshold. Okay? So this is very conservative. Are we together? This more or less? Okay. So if I know that the vast majority of the time, so if I put in a big value of k, like 3, then I know that 8/9 of the time, at most 1/9 of the time, the sample percentage is going to be further than 3 times this away from the population percentage. Well, let's suppose that, so let's draw this again. Here's the population percentage p. And let's say that this is now p plus or minus 3 times f times a half over root n. So this is 3 times f times a half over the square root of n. And that's p plus that. And this is p minus 3 times a half, times f over root n. Okay, so what do I know? I know that 8/9 of the time, my sample value phi is going to be in here somewhere. And at most 1/9 of the time, it's going to be out here or up here. Right? Okay? So if I'm in one of those sort of 89% of the time samples where the sample percentage is in this range, what happens if I take the sample percentage and I go up and down from the sample percentage by this amount, 3 times f times a half over root n? Well, if I'm closer to p than this limit, then when I go down by that amount, I'm going to trap p. I'm going to go up to something like that. I'm going to go down to there, and I'm going to cover p. If I'm in here, then if I go up and down by this amount, I'm going to include p and include some junk up there, right? And if I'm down here, again, if I go up by that amount, I'm going to include p, and I'm going to include some junk down here. Right? So whenever the sample percentage is in this range, an interval around the sample percentage of this width is going to include the true value. Okay? If I'm within 3f times a half over root n of the truth, then I'm within 3f times a half over root n of the truth. And so it doesn't matter whether I measure from the truth to the estimate or from the estimate to the truth. If I'm within that distance, I'm within that distance. Okay? So if I report it as my interval The lower endpoint is this minus 3 times f times a half divided by the square root of n, and as the upper endpoint of the interval, phi plus 3 times f times a half over root n. This is a random interval, right, because it depends on phi, and phi is a random number. Phi depends on the sample. It's the sample percentage, okay? So this is a random interval. It's centered at phi. It goes down from phi by this much. It goes up from phi by the same amount, right? Okay. So this interval is random. Sometimes it's centered at a point that's up here. When that happens, the interval is going to miss the truth. Whenever it's centered at a point in this range, it's going to include the truth. So whenever it's centered at a point in this range, it's going to cover the true parameter value. So this is a confidence interval for the true population percentage p, and the confidence level associated with this, the fraction of the time that that interval is going to include the truth, is going to be at least what? Right? It's at least 8/9. At least 8/9 of the time, the sample percentage is this close to the population percentage. Whenever that happens, this includes the truth. Okay? Some of the time it isn't, and then it doesn't include the truth. Let's do a little. Okay, so what do we got? We have a 0, 1 box. In this case, there's 3 zeros and 3 ones. And we're going to sample without replacement. We're going to take a sample of size 3, and we're going to go up and down from that by 2 times our bound on the SD of the box. Sorry, 2 times our bound on the SE of the sample percentage based on the bound on the SD of the box. And in fact, in this case, the box does have 50% zeros and 50% ones, and so that bound is sharp. So if we do this, and we take a sample, this time, when we went up and down by twice our bound, that interval missed the truth. This time, the interval included the truth. This time, it included the truth, et cetera. Right? So whether we include the truth or miss the truth depends on what value we get for the sample percentage. All right? So if we do this over and over and over again, this is going to include the truth most of the time. How often do we know it's going to include the truth? Okay, if we're going up and down by twice our bound on the standard error, chance that things are beyond that is at most 1 over 2 squared, right? 1/4. So this ought to include the truth at least 75% of the time. What actually happened, it included the truth 88.5% of the time. Okay, so it's conservative. It includes the truth at least as often as we claim that it will. Okay? All right, so we'll continue this next time.